Okay, so thanks for the invitation to submit a talk. So I'll talk about this work with my collaborators, James Bonifacio, Laura Johnson at Case. Laura's just graduated and headed to Europe. Austin Joyce, who's at Amsterdam, and Rachel Rosen, who's at Columbia. And I'm going to be talking about things that are in these two papers here and another paper to come shortly soon. So this is about classifying the types of shift symmetries that you can have on de Sitter space and anti-de Sitter space that generalize ordinary shift symmetries and Galileons and so on. Okay, so by way of introduction, we have a shift symmetry whenever we have a spontaneously broken global symmetry, so a Goldstone boson. So the typical example is your Mexican hat potential here, and there's a unbroken direction here in the angular direction, and the field that parameterizes that angular direction has a shift symmetry which just moves it around that symmetry direction. So the leading order symmetry transformation of that Goldstone is going to be a constant. This is quite general, so anytime you have a spontaneously broken symmetry, the leading part in powers of the field of the symmetry transformation is a constant, and then there can be higher order parts as well. And this tells you that the vacuum is broken, that the field configuration where the field is equal to 0 is not preserved by this transformation. On the other hand, an unbroken symmetry is one which does not have this constant piece out front, and this preserves the vacuum. Because of this constant piece, the leading order Lagrangian, the second derivative part, always has to be a massless kinetic term like this if we're limited to two derivatives. So it tells us that the leading part of the Lagrangian is the ordinary kinetic term. If we ask about interactions now, suppose that we want to fix the full exact shift symmetry to be just this leading order part, just the shift by a constant. In that case, we can parameterize all the possible invariant terms, interaction terms that we could have. So anything that involves at least one derivative acting on each field is going to be allowed. So these are the invariants, if you like, under this symmetry, derivatives of the fields. So we can have an arbitrary function of these invariants. So these, in some sense, are the boring interactions that are exactly invariant under the symmetry. But there's one particular interaction which is interesting. It's not exactly invariant. It's only invariant up to a total derivative, and it has fewer derivatives per field than any of the actual invariants. So this is known as the Wess-Zumino term. In the case of a simple shift symmetry like that, it's just the linear and phi term. If we look back at this kinetic term, it has more than just the shift symmetry. It actually has an infinite number of symmetries, as we'll see. So there's a symmetry where we shift the field by a term which is linear in the space-time coordinate. So x mu is the space-time coordinate, b mu is some constant vector. If we shift by this Galileon-like transformation, we'll find that this is invariant up to a total derivative. And now there are boring interactions where I can write down any function of things that have at least two derivatives on each field. So there's an invariant building block, which is two derivatives of the field, and it's exactly invariant under this shift, and these are, in some sense, the boring interactions. But there's a finite number of interesting interactions which have fewer than two derivatives per field. These are the so-called Galileon interactions, or Wess-Zumino terms. So there's precisely 5 of them here in 4 dimensions. In d dimensions, there'd be d plus 1 of them. And they have fewer derivatives per field than any of these boring interactions. There's also another possibility where instead of just taking this pure shift here as the symmetry, we allow it to deform by terms higher order in the field. And the requirement of closure of the algebra and so on, it fixes this deformation. There's only one possible deformation, which is this one here. And if we ask for interesting interactions under this deformation, it leads to dBi Lagrangian. If we go back to the kinetic term and now ask for higher order symmetries, higher in powers of the space-time coordinate, we find that this kinetic term is invariant under this kind of shift here, where we have a symmetric traceless tensor times 2 powers of the space-time coordinate. So we'll call this the extended Galileon symmetry. There is one interesting term that's invariant under this. So there's, again, the boring terms where we'd have at least 3 derivatives per field, but there's this interesting term where we have, which just looks like a Galileon, but now there's only one possible term. And in fact, it has to be deformed nonlinearly. So there's this nonlinear extension of the Galilean symmetry, of the special Galilean symmetry, which leads to this theory which is completely fixed up to this one interaction scale here. So this is known as the special Galilean. So it's more symmetric than the ordinary Galilean. It also has the Galilean symmetry and the ordinary Galilean symmetry and the shift symmetry. We could try to go further. So the kinetic term has, in fact, an arbitrary symmetry where we allow arbitrary powers of x multiplied by symmetric traceless constant tensors. But there doesn't seem to be any interesting interactions that you can write at higher than second order in powers of x. So if we allow for these cubic terms, for example, you can always write those boring interactions with multiple derivatives of the field, but there's no interesting Wessumino-like terms or special Galilean-like deformations. Okay, so that's basically the story for shift symmetries of scalars in flat space. So our goal is going to be to extend all of this to de Sitter space and anti-de Sitter space and to the higher spins to see what the analogous classification looks like. Okay, so the technical tool we'll need is the embedding space formalism. So we'll think of de Sitter space as embedded in a Minkowski space of one higher dimension. So these big X's are some ambient space, and then there's this hyperboloid of radius r, which is the de Sitter hyperboloid. And when you restrict things to the de Sitter hyperboloid, you get the intrinsic description, but we can talk about everything in this embedding space description where the de Sitter symmetry is manifest. So when we do this, there's a one-to-one correspondence between tensors in this embedding space that satisfy a transverseness condition and a homogeneity condition with some homogeneity degree mu, and tensors on the de Sitter space itself. So then once we have this set up, there's rules for how you project down derivatives and so on, and any expressions in the ambient space you can bring down to the intrinsic space and vice versa. Okay, so let's start with the scalars. So if we have a massless scalar now on de Sitter space, so now this is the massless Lagrangian on de Sitter, it still has a shift symmetry. Putting it on de Sitter space doesn't spoil the shift symmetry, at least with just the kinetic term here. But the higher symmetries, the higher shifts and higher powers of x are all broken. So this now only has the shift symmetry. It turns out that there's a special value of the mass, which is this value here. So h is the Hubble constant of the de Sitter, capital D is the space-time dimension of the de Sitter. If you put exactly this mass value in, then this will now preserve a Galilean symmetry where we have a shift of the field which is in embedding space looks like this. So this S here is now some 5-dimensional constant tensor which multiplies the 5 embedding space coordinates. So there's 5 symmetries of this theory for this particular mass value. And if we take the flat limit, the 5 symmetries in this embedding space, when we go down to the intrinsic description, this vector turns into a vector plus a scalar, and the lower dimensional vector it turns into is, you can think of as the Galilean symmetry, and the lower dimensional scalar is the shift symmetry. So this is kind of taking what were the symmetries of the flat space Galilean theory and merging them up into higher dimensions, and where we get this, we need this non-trivial mass. There's another value of the mass, this one here, where we get a special Galilean-like shift symmetry in the embedding space. So now we have this quadratic in embedding space coordinates, and when we take the flat limit, this reduces to the special Galilean symmetric tensor, the vector, and scalar, which are precisely the symmetries of the special Galilean in flat space. Okay, so in fact, there's a whole sequence of mass values. So they're labeled by this integer k, going from 0, 1, 2, and 3. These mass values here, where you get a kth order in x shift on ADS or de Sitter. So k equals 0 is the ordinary shift, k equals 1 is the ordinary Galilean, k equals 2 is the special Galilean, and in the flat limit, it reduces to precisely the symmetries of that particular case. And you can think of these mass values as coming from the higher dimensional Laplacian. So if I take a higher dimensional massless field satisfying a Laplacian equation, and I project it down, because of that non-trivial homogeneity requirement, you're going to generate a mass term, and depending on what homogeneity you choose, you'll get different masses, and certain homogeneities will be consistent with these symmetries, and that's what leads to these mass values. Okay, a similar thing happens for all the higher spins. So here is now the equation of motion, the Klein-Gordon equation that governs a spin S field on de Sitter. And there's particular mass values here, labeled again by this K, for each particular spin, where you get enhanced shift-like symmetries. So for a higher spin field, the shift-like symmetry you get for a particular value of K is encoded in this, this symmetric traceless tensor, where the symmetries are those of this particular Young tableau. So here's what it looks like from a dual CFT point of view. So if we talk about the dual CFT operators that are dual to these shift symmetric scalars and higher spins, here's what the picture looks like. So here we have spin going along the bottom, and the conformal dimension, which is basically the mass going up the vertical axis. So for the scalars, here are the dots represent all these special shift values. So at this value here is the massless scalar, here's the Galileon, here's the special Galileon, and the generalizations going up. For spin 1, this would be like a shift symmetric vector, a Galileon vector, a special Galileon vector, and so on for all the higher spins. So the label K telling us how the depth of shift, if you like, is going horizontally like this. Okay, so we can understand the existence of these shift symmetric fields as the reason they're there is essentially because they're longitudinal modes of partially massless fields on the de Sitter space. Okay, so just to review what partially massless fields are, so if I have a massive spin S field on de Sitter, satisfies this equation. At special values of the mass, there are going to be enhanced gauge symmetries. So here are these special values of the mass. They're labeled by a parameter t, which is the depth. And at depth t, it becomes invariant under a gauge transformation, which has a gauge parameter with t indices, with the rest of the indices filled out by derivatives. So when t is equal to s minus 1, that's the ordinary massless degree of freedom, and then these other depths are partially massless degrees of freedom. So these gauge symmetries reduce the lower helicity components of the massive field. So a generic spin S field has helicity components going s minus 1, and so on all the way to 0. And if I have a depth t partial masslessness, then it means that the first t helicities are all being gauged away. So here's what the partially massless fields look like from the CFT point of view. So there's these dual CFT operators at these particular values of spin and conformal dimension delta. So they happen on ADS, they happen all in the non-unitary region. On de Sitter, they are unitary. So when you're at one of these special partially massless points, what's happening is that there's a null state that happens in the Verma module if you have one of these things as a conformal primary. So there's a null state at level s minus t, which is essentially gauging away those lower helicities from the bulk point of view. Okay, so what's essentially going to happen is that these null states are breaking off and forming a separate representation, and those are going to be the shift symmetric fields that we saw. Okay, so how do these shift symmetries arise from the decoupling of the null states? So as an example, let's consider just a simple massive vector. So this is the simplest case. So here is the Lagrangian for a massive vector, a Proca field on our ADS space. So here's the Maxwell field strength tensor part, and here's the mass term a squared part, which breaks the gauge invariance. So this theory by itself at generic values of n has no particular symmetries at all. As we take the m goes to 0 limit, we recover gauge invariance. So to maintain continuity in the number of degrees of freedom, we have to introduce a Stuckelberg field. So we follow the standard prescription of introducing a Stuckelberg field by patterning it after the gauge symmetry that's broken by the mass. So we introduce a phi like this. And once we introduce this phi, we get a gauge symmetry, which is the usual one on A, and then a shift by the gauge parameter of phi. So this lambda here is a gauge parameter. In the massless limit now, we recover then a ordinary massless vector and an ordinary massless scalar, and the gauge symmetry in turn falls off of phi because of this m here. So we're left with no gauge transformation on phi and the standard gauge transformation on f. Okay, so again, we don't seem to see any shift symmetry that's arising, but we notice that the Lagrangian for phi here does have a shift symmetry. So where is that shift symmetry on phi actually coming from when there was no symmetry at all to begin with in the massive vector Lagrangian? Okay, so this takes us to the reducibility parameter. So a reducibility parameter is a value of the gauge parameter lambda such that the gauge transformation vanishes. So we're looking for lambda such that d mu of lambda here is equal to 0. If we have such a lambda, then in fact this can survive the massless limit, because over here we can, if lambda is chosen to be the reducibility parameter, then this part vanishes here, and we can then rescale lambda to absorb this m and take a limit where lambda hat here, which is the rescaled reducibility parameter, is kept constant. And so in that limit then, this is exactly the shift symmetry that appears on phi. So the shift symmetry is precisely the reducibility parameters of the gauge symmetry that we are restoring. Okay, so as a next non-trivial example is, let's consider the massless limit of massive spin 2. So if we have a massive spin 2 field on de Sitter space, we know that we'd like to restore the diffeomorphism invariance, the linearized diff invariance that appears when the mass goes to 0. So here's a little picture of the mass versus Hubble radius plane of a massive spin 2 on de Sitter space. So when m squared is equal to 0, this vertical line here, that's when we're recovering the diff symmetry of GR. So we're going to be asking for a massless limit where we go like this. So keeping the ADS radius fixed, but sending the mass to 0. So when we do that, we have to introduce a vector Stuckelberg field, because that's patterned after the gauge symmetry that we're trying to restore. So we reintroduce this vector field A mu, and now there's a gauge symmetry that shifts A mu. And in the massless limit now, we get a massless graviton plus a proto-Lagrangian for a massive vector for this field that we introduced. So the decoupling limit theory here is a massive vector with a particular value of the mass. Again, the gauge transformation seems to go away, but we should look for a reducibility parameter to see if there's a hidden shift symmetry of this Lagrangian. So indeed, there is a reducibility parameter if C is such that the gauge transformation is 0, which is precisely a killing vector on the ADS space. Then this transformation vanishes, and we can rescale the transformation on A to make it a simple shift. So this proto-Lagrangian for this particular value of the mass is in fact invariant under a transformation where we shift A by a ADS killing vector. So the ADS killing vectors can be parameterized by an embedding space by some big antisymmetric tensor. And that antisymmetric tensor will indicate by this Young tableau here. So there's 10 of these symmetries for 4-dimensional de Sitter. Okay, now let's look at the partially massless limit. So now we're going to be taking the limit where we go towards the partially massless line here. So the gauge symmetry that we need to reintroduce is the partially massless gauge symmetry, which looks like this here, this double derivative thing. So we need to introduce a scalar Stuckelberg field now, which parameterizes the partially massless symmetry that we're trying to reintroduce. And to canonically normalize everything, I have to put this particular combination out front. So this epsilon here is going to be measuring how far away we are from the partially massless point. So we're going to be taking the limit epsilon goes to 0 with Hubble kept fixed. And in the partially massless limit, when we do this, we find a partially massless field plus this scalar field with a particular value of the scalar mass. And that particular value of the scalar mass is precisely the value we saw for the ordinary Galileon on curved space. So indeed, there is a reducibility parameter for this gauge symmetry. If I choose the shift in phi to be precisely linear in the embedding coordinates, that parameterizes these reducibility parameters, and it tells us that this Lagrangian with this particular mass that comes out is invariant under a shift parameterized by these ambient space vectors. Okay, so the general pattern then for any spin is if we take an arbitrary massive high spin and we approach one of these partially massless points, there's going to be a gauge symmetry that appears at the partially massless point that we have to parameterize with some Struckelberg fields. And those Struckelberg fields are precisely these shift symmetric fields. So the reducibility parameters that we have to find now will tell us about the shift symmetries. And the reducibility parameters, it turns out, are classified by generalized killing tensors. And there's a finite space of solutions to this generalized killing equation here. So it's like the killing equation with more derivatives here, anti-symmetrized. And the space of solutions is parameterized by precisely this Young-Teplo that we saw parameterizing the shift symmetries earlier on. So this explains where these shift symmetries are coming from. They're just the reducibility parameters of the partially massless gauge symmetry that's coming in. Okay, so here's the picture now with our partially massless fields in blue, our shift fields in black. And from the CFT point of view, what's happening is you have this generic Verma module for the CFT, and as you approach one of these partially massless points, one of these null, you get one of these null modules developing, and that null module is precisely the module for one of these shift symmetric fields. So the one it corresponds to, you can tell by flipping around this diagonal line. So here, for example, is the photon, so spin 1, massless spin 1. So if I flip around this line, then this tells us that the longitudinal mode is precisely the shift symmetric scalar. Here's the graviton. If I go around this line, the longitudinal mode is the k equals 0 vector. Here's the partially massless one. Its longitudinal mode is the k equals 1, the Galileon scalar. And for all the higher spins, it's just flipping around this line. And then along this diagonal, there are these special points right along this diagonal. We don't really know what special properties they have in terms of symmetries or anything like that. But in the case of D equals of CFT3, this scalar case happens to be the conformal scalar. But that's not true in higher dimensions. So we don't yet know what's special about any of the fields on these lines. Okay, so now the question is, are there interactions that preserve these shift symmetries? So everything I said up to now about the classification was just for the free theories. Okay, so to ask about interactions, the first thing we should ask about is the algebra of symmetries, to ask whether there can be non-trivial algebras. So when we introduce interactions, we're still going to have the ADS isometries, so we don't want the de Sitter ADS isometries to be broken. So we want, so this is the way the de Sitter symmetry acts on a scalar, for example, in embedding space. We want that to remain undeformed. So the commutators are just going to be the de Sitter algebra. The shift symmetries, on the other hand, can be deformed. So the leading part of the shift symmetry is going to be just the shift by this symmetric traceless tensor in embedding space, but now we're going to allow for possible deformations which involve powers of the field. The shift symmetries are themselves tensors under the ADS isometry, so that fixes the commutator of the ADS generators with the shift symmetries. So the only commutator which is not yet fixed is the commutator of two of these shifts with each other. So it turns out that there's only one possible structure that can appear in terms, if you just look at the symmetries of these indices and antisymmetry of the commutator. So here's the one possible structure that can appear, and there's one coefficient alpha that can appear out front. Then we have to make sure that the Jacobi identities are satisfied, and the Jacobi identities tell us that for k greater than 2, so for more than the special Galilean, there's no possible alpha. Alpha has to be 0. So we only get interesting non-trivial algebras when k is equal to 1 or 2. And then there's no constraint. The Jacobi identity is satisfied. Okay, so we can always have boring theories where we just take the algebra to be trivial, where this alpha is 0. So these we'll call abelian theories by a misnomer. So when alpha equals 0, the shift symmetry just has its linear part. There's no corrections with any powers of the field. And now we can construct interactions by building these invariant building blocks, which just in embedding space are symmetrized powers of the fields, which when you reduce down give you some symmetrized covariant derivatives with some order h stuff. And we can build Lagrangians, which are arbitrary functions of these building blocks. And these theories will generally be ghostly and so on, but in certain cases, there'll be a finite number of Wess-Zumino terms which have fewer derivatives than these building blocks and which are ghost-free. So for k equals 1, again, this is like the Galileans. There's a finite set of interactions which are ghost-free. It turns out that in this case, they can be made out of the building blocks. So what happens is the leading order derivatives all get anti-symmetrized away, but that higher order and h stuff survives and gives you a non-trivial Lagrangian. Okay, so these were known as the ADS Galileans. So we wrote them down a while ago from completely different, from a completely different direction. So in the non-abelian case, so for k equals 1, there's this possible deformation. So the algebra looks like this, and the shift symmetry now that realizes the algebra looks like this. So in terms of the generator space of generators now, we have the ADS isometries themselves, which are parameterized by an antisymmetric tensor, and then we have the shift symmetries, which are parameterized by a vector in embedding space. And if we put these together now, we can put together the shift, the antisymmetric tensor and the vector into an antisymmetric tensor of one higher dimension, and then we find the algebra is just the ADS algebra of one higher dimension. So what this is realizing is a symmetry breaking pattern of some whatever real form of SOD plus 2 down to the ADS algebra SOD D plus 1. So this is what gives ADS DBI Galileans, the DBI type theories, which again we wrote down, have been written down a long time ago from other considerations. For k equals 2, again, we find there's one possible deformation of the algebra. So this is what it looks like now. Here's what the transformation looks like for with these higher powers of the field. So now the generators are, again, the antisymmetric tensor for the ADS symmetries and a symmetric traceless tensor for the shifts. So now we can combine these two. We can combine the antisymmetric and the symmetric tensor into a traceless tensor. And the traceless tensor M has this commutation relation, which is precisely the commutation relations for SL D plus 1, whichever real form you're talking about, depending on whether you're an ADS or DS or Euclidean or Lorentzian. So now we have a symmetry breaking pattern of SL D plus 1 down to SO D plus 1. Okay, so here's what the Lagrangian of that theory looks like. So the k equals 2 theory, it's like the ADS version or the DS version of the special Galilean. So here it is written down for de Sitter space. So the Lagrangian, it looks like a mess. So here, this is all on de Sitter space. These x's are various combinations of this tensor M, which is given by this double derivative of the scalar, and x is like the kinetic term, and y is this mess here, and h is the Hubble constant. So there's two parameters here. There's the Hubble constant h of the background, and then there's lambda, which is like the interaction scale. But other than that, everything the structure is completely fixed by this nonlinear symmetry. So at leading order, if I look at expanding it in powers of the field, it has the correct mass to be that shift symmetry with k equals 2, and then higher order terms all have a structure which looks like Galileon's with the most powers of derivative, and then order Hubble stuff as you go down in derivatives. So the flat space limit reproduces the special Galileon, but you have this non-trivial order Hubble stuff that appears away from flat space, which is essential to maintain the symmetry on curved space. So what's interesting is you now have a non-trivial potential. Because of this order H stuff, there's terms which survive even when the field is constant. So there's a potential which looks like this. Here's the shape of the potential. It's Z2 symmetric. The whole theory is Z2 symmetric. And it has this funny pattern of minima and maxima. So when we're expanding around phi equals 0, we're expanding around a maximum. That's telling you that phi is a ghost. So in fact, all these special mass values, they're wrong sign on de Sitter space. We actually think they're still stable. They should actually be, they're in the list of unitary de Sitter representations. So we have reasons for why we think these are stable. On ADS, everything's just flipped upside down, so it's definitely stable there. But then we also have these other minima here that break the Z2 symmetry. So if you'd expand around those minima, you'd be reordering the whole set of terms, but it would be the same. The shift symmetry would still be there in some disguised form. Here's what it looks like in arbitrary dimensions. So this complicated mess. Again, the flat space limit is just the special Galileon. The expansion in powers of fields reproduces the correct mass for k equals 2. And here's what the potential looks like in various dimensions. So in p equals 4, this is what we were just looking at, but then as you go up in dimensions, you get more and more kind of wiggles in the potential, more and more critical points. Okay, we can ask, so that's basically the whole story for interactions of just a single scalar. We can ask for now vectors. If we have a single vector, it's also possible to get non-trivial interactions. These we can think of as coming from a decoupling limit of nonlinear massive gravity on anti-de Sitter space. So there are ghost-free versions of massive gravity, and if you take the decoupling limit of these full nonlinear massive gravities, as you keep the ADS radius fixed, and as you send the graviton mass to 0, the longitudinal modes split apart now into an interacting theory. And the non-abelian extension of the shift symmetry looks like this. So at 0th order in the fields, it's just a shift by a killing vector, but then you get these higher order terms, powers of the field. And the algebra this forms now is a direct sum of two de Sitter algebras. So one is the isometry algebra of the background, and the other is the SOD plus 1 of the shifts of the killing vector. So together it's the direct sum of the two, and the symmetry breaking pattern is taking you down to a diagonal of these two. Okay, so as far as classifications of the algebra are concerned, we have reason to suspect that there are other non-trivial theories that are out there just based on the algebra. So there was this paper a few years back by these people where they were looking at various higher spin algebras, and there are certain truncations that appeared in these higher spin algebras. So what we're looking at here is a sequence of algebras. So each line here is its own kind of algebra that closes on itself. This first one here, this is precisely the algebra that we saw for the special Galileon on curved space. So this antisymmetric tableau here was the isometries of the background, and then here's the symmetric traceless tensor of the special Galileon. So these together we saw formed an algebra, and the non-linearly realized symmetry operates on this single scalar field, the k equals 2 scalar. So the existence of this algebra kind of explains the existence of this scalar Lagrangian. But next on the list is this complicated algebra. Again, we have the ADS isometry here, but now we have a symmetric traceless tensor, which represents the k equals 2 scalar. We have a rank 4 symmetric traceless tensor, which would be a k equals 4 scalar. It would be the shifts of a k equals 4 scalar. We have this hook thing, which has the correct generators to be the shifts of a k equals 2 spin 1, and this window tableau, which is the right thing to parameterize the shifts of a k equals 0 spin 2. So we think there should be some theory. So taken together, all these generators, we're told, actually close into an algebra. So there should be, we think, some theory which has an interacting k equals 2, k equals 4 scalar, and vector, and spin 2, which probably has some horrible Lagrangian with all of them interacting together and all of them transforming under this giant algebra, which spontaneously breaks down to just the ADS. And here's the next thing in this list of algebras that they found. So in this theory, we'd have 3 scalars and 2 vectors and 2 spin 2s and a spin 3, and it just goes up in spin. And if you can take the limit to infinity of this sequence of vectors, maybe there's a shift symmetric theory with infinite towers of fields, which you could think of as some kind of longitudinal mode where you take a theory like you can imagine string theory, which is a theory of massive high spins, and you take like a massless limit where the string scale is being set to 0, and it becomes a Vasilyev-like theory of massless fields, and some longitudinal modes decouple. That giant theory of an infinite number of longitudinal modes could be some giant shift symmetric theory with whose algebra is the limit of all this. So that's all speculation at this point. Okay, so in summary, we've classified all the massive fields of all spins on ADS that develop shift symmetries at particular values of the masses. And they are labeled by these various depths, which generalize the shift Galileon, special Galileon, and so on sequence. So we've done the bosons. We're in the process of doing the fermions. So there should be a similar story for all the fermions and supersymmetries. So how all these things interplay with supersymmetry is quite interesting, and we're working on that at the moment. So these all correspond to longitudinal modes of partially massless fields. We've found the interactions that we think exhaust the case of just a single scalar or vector, but we think that there are these other more complicated multi-interacting examples that realize these more complicated algebras. So what we really need is a way to show these theories exist, or to find the interactions without having to actually construct these Lagrangians, because even in the scalar case, constructing this Lagrangian was a giant nightmare, and there's no way it would be able to do it with these higher multi-fields and so on. Okay, I'll leave it at that. Thank you.